Well, hello everybody, Dave here, and now that we've done a lesson on figuring out what sampling distributions are, let's go ahead and focus on the type of data that we have and the type of distribution that we'll get. First up, we'll deal with categorical data and the idea of sample proportions. So let's imagine we're trying to find the number of orange Reese's Pieces in any given vat of Reese's Pieces. If you look at the screen, you can see that the value of the sample size is different for each of these distributions. The number of samples is the same, and you can see that that value, which is listed like a pi, but it really means p for the parameter of interest, the center of the population, is supposed to be the proportion of 0.45, meaning that there should be 45% of the candies are orange. Well, you can see that on each side there's a sample that's listed as an orange value. In the case on the left, it's 0.48, and in the case on the right, it's 0.46. So you can tell again from the variability of sampling that you're not going to end up with 0.45 every single sample. But what we also know is that if we keep taking repeated samples again and again and again, and we plot those statistics on the horizontal axis, what results is the distribution like you see before you, which looks suspiciously like a normal distribution. In this lesson, we're going to learn how to actually justify the use of that through the use of conditions, specifically the random condition, the 10% condition, and the large counts condition that you've learned back in Chapter 6. So you can see again that if we look at these distributions, they are centered right on 0.45. And although there's an obvious standard deviation associated with these distributions, both of them inevitably ended up centered on the parameter of interest. The same would be true if instead of 0.45, we're looking for something like 0.15. Again, the sample sizes are different, and you can see again that we have distributions that are approximately normal and centered right on the parameter of interest, which in our case is 0.45. The one thing I would like to point out again is if we're dealing with the spread of these distributions, you can tell that the spread of the distribution on the right is a little smaller than the one on the left, and that's going to become extremely important because when we decide how much is enough but too much is a bad thing with that idea of 10% condition, well, how much is enough is going to be determined by exactly what kind of spread are we looking for with our sampling distribution. So there's a few things that I want you to notice about the sampling distribution that I think are worth mentioning. The first of course, is the shape. And as I've alluded to, we're going to go ahead and justify this as a normal distribution with the conditions that I've listed a couple times. And in that case, you can tell that the population parameter of interest is the center of that sampling distribution. So there's something special about the way that we're doing this sampling and the way that we're building the distribution that's allowing us to say so. So shape and center are taken care of. With spread, you can tell that both the parameter of interest as well as the sample size are going to have a factor on exactly how spread out these things are. So as a reminder, if we go back to the original definition of what a sample proportion is, we take the size of the sample and we count the number of successes within that sample. That's the basic definition of probability that we used way back in Chapter 5. But now we're a little smarter, we're a little wiser, and we're going to go ahead and label a random variable as our number of successes. We're going to use small n as our sample size as we always have. And now instead of thinking about the sampling as an individual sample, we're going to talk about it as a transformation of a distribution from a singular sample to the entire distribution itself. And so back in the previous chapter, we learned that there's a binomial distribution. And with a binomial distribution, we defined the mean of a random variable to be n times p, and the standard deviation of a binomial distribution to be the square root of n times p times 1 minus p. And I wanted to remind you that p is the proportion of successes, and 1 minus p, the complement, is the proportion of failures. Well, as I said before, if we consider this as if we are transforming the distribution by multiplying it by a constant, in this case 1 over n, well then really what we're doing is we're taking our original binomial distribution and we're going to multiply it by 1 over n to get the center of our sampling distribution for proportions. And so you can see that the next line here is mu of p hat. That literally means the mean of the p hats distribution, which is the center of our sampling distribution. So this is an important notation to recognize. And if you take your mean of a binomial distribution, which is n times p, and you multiply it by 1 over n, which again is just taking our successes and multiplying it by 1 over n instead of just saying that it is, look what happens to the n. You cancel the n out, and what you get is the center of our sampling distribution of sample proportions is actually equal to p, which is the parameter of interest, the center of our population distribution. Likewise, if we want to find the standard deviation of our sampling distribution, we can take the original standard deviation of the random variable x, and we can transform it by multiplying it by 1 over n. When you do so, we do a little fancy algebra, and we end up with the square root of p times 1 minus p divided by n. Well, there's two important elements here that we already figured out from looking at the original pictures of the Reese's Pieces example, and that's the center is by definition now going to be the parameter of the population, and the standard deviation of the sampling distribution is actually related to the square root of 1 over n, specifically meaning that as the sample size increases, the spread will decrease. Well, this is an important element now to our sampling distribution because this is, for the first time, a piece of evidence that tells us that a larger sample size we take, the smaller the spread is going to be for the resulting sampling distribution, which is what we're going to use to make a meaningful statistical conclusion. And so to summarize all that we've talked about so far, we can see now that there is a list of things that we now know about the sampling distribution simply because we understand binomial distributions from the previous chapter. The first, of course, is that the center of our sampling distribution is equivalent to the parameter of interest, which in this case is the population proportion. You can see the notation that says mu of p hat because we're talking about the distribution of p hats. Now, instead of just graphing the proportions, we're graphing the sample proportions. We've also seen that standard deviation can be calculated using a transformation of the binomial distribution standard deviation simply by transforming it by multiplying by 1 over n. And when you do so, you can see now that the sample size will change the standard deviation, whether it be a larger one to shrink the standard deviation or a smaller sample size to increase the standard deviation. Clearly, you don't want to increase the standard deviation. However, the only way that we can use these equations is if we satisfy the previous conditions that we needed to discuss a binomial distribution and approximate it to a normal distribution. So the first one, of course, is if random sampling has taken place. None of this is possible without random sampling. But in order to use this standard deviation equation, we have to satisfy the 10% condition because now what are we doing? We are sampling from the population. And remember, the 10% condition is a test of independence. And so the idea is, yes, in actual fact, we are sampling from a population without replacement, which means we are inherently changing the proportions. What we're saying here is that the sample size that we've taken is not large enough to drastically alter the proportions of the population, thus meaning that we are satisfying this requirement of independence to use this binomial distribution equation. Finally, and perhaps the most importantly, is now we have to justify the use of the normal distribution. So we've satisfied the fact that it's going to be an unbiased estimator with random selection. We've satisfied the fact that it's going to have a standard deviation as listed because we are sampling without replacement, but we are satisfying independent nature of these samples. But in order to justify the shape as being normal, we're going to satisfy the large counts condition. And in that case, it's the product of the sample size times the successes and the sample size times the proportion of failures. And both of those have to be greater than or equal to 10. If one of these fails, then the entire condition fails and you can no longer assume it to be normal. In those very, very rare cases, all that means is you have to go forward with binomial distribution calculations. So this is a summary in a graphic form of exactly what we're doing to build the sampling distribution. And we had something similar in the previous lesson, and we'll have something similar in the next lesson. But the idea, of course, is we have a population with some sort of proportion P of successes. Notice that it's a script P. And from that, we're going to take an SRS of size n. Notice that it's going to be the same size n, and you can understand why now. If you change the sample size midway through the study, what you're going to do is you're going to drastically alter the way that the sampling distribution will converge on this center of interest. And therefore, if the spread is changing, you have no choice but to stick with that original sample size. So don't change sample sizes when you're doing an SRS at any point, or else this shape is never going to converge nearly as quickly as it will if you stick to the regular size n. So you take a sample proportion and you graph it on the horizontal. We know there's variability in sampling, which means we're not going to get all samples to be centered right on the value of interest. However, if you take enough samples, this distribution will begin to form. This normally distributed set of sample proportions will result in a center. The mean of the sampling distribution is actually centered on the parameter of interest, which in this case is script P. And what is the standard deviation of this distribution? Well, it's the calculation involving the sample size. So you're going to run into a case now where you run into a bunch of different formulas that look really, really similar. So I encourage you to really understand how we got this equation by transforming a binomial distribution simply by multiplying it by 1 over n, so that now we were talking about proportions and sample proportions at that in terms of a random variable divided by the sample size. So this distribution is built through an immense understanding of statistics and the various rules that we've learned up till now, and it's important to brush up on those before you move forward. If we go through an example problem, I would normally give this as a blank, but I don't want to use a tablet, so we're going to go ahead and just show it typed out for you. Government data shows that 76% of grade 1 students read at their grade level. An SRS, so simple random sample of 300 inner city Vancouver grade 1 students, is taken. What is the probability that less than 70% read at their grade level? So when you see a question like this, the first thing I want you to key in on is that they tell you that's an SRS. So that's an important element. The second thing is obviously they give you a sample size. And the third is that they tell you a percentage. Now that percentage is coming from government data. It's reasonable to assume that this is a survey of the population, which means that value 76 is actually going to be the parameter of interest. Now, because we're dealing with proportions, you don't want to write it as 76%, you want to write it as 0.76. Now, when they ask you what is the probability that less than 70% read at their grade level, what they need you to do now is build the sampling distribution. And so we go through the motions. We understand that the center of the sampling distribution is going to be 0.76, as we discussed previously. We're going to calculate the standard deviation of the sampling distribution by using the sample size and the proportion of successes and failures multiplied together to get the value that we see, 0.0247. And then when it's time to find the probability that a given sample is going to result in 70% less read at their grade level, we're looking for the probability that p hat is less than 0.70. Well, we use TI calculators, and for this I would do a simple normal CDF. And we would use the lower bound as extremely low, upper bound to the 0.7, with the mean and standard deviation that's given to give you a very low number of 0.0076. Now, there's a couple of things here that are important to recognize. First and foremost, you have to show the labels for normal CDF, or else it's considered calculator speak, and that's bad. The second thing I want you to notice is that though we were given information from the question, we have to justify the use of that information. So they gave us the parameter of 0.76, but you'll notice that I've labeled it as mu of p hat is equal to 0.76. So I'm making it very clear that these two are equivalent to each other. So don't gloss over that idea. In more difficult questions, they might actually give you the standard deviation of the population, and students are often confused of which standard deviation to use. Just remember that if we're talking about the sampling distribution, you have to calculate the standard deviation using the equation that you see before you. But out of all this, there's one important element that I've left out simply because I didn't have the space to write it down, but you should certainly make note for yourself, and that's the biggest question of all, of why can we do any of this calculation at all? And if there's one thing anybody's learned from me as a teacher in statistics, it's that you have to justify the use of anything that you use within this course. So we are assuming that the sampling distribution is normal. But I've mentioned multiple times now, there are conditions that you have to satisfy in order to do this. The random selection condition, the 10% condition, and the large counts condition. Without those being satisfied, you don't get to use the normal distribution at all. So as an extension to this question, a thing that you would have to use way before you do any of these calculations, you would have to satisfy that the conditions have been met to approximate your sampling distribution as a normal distribution with the center and spread as you see here. For part B, this is more of a do I understand what statistically significant means? The calculation is exactly the same, except for we obviously don't need to calculate the mean and standard deviation anymore, but we get an outlandishly small number. And you are right at the edge where we're going to start discussing it for real, what it means to be statistically significant in terms of these probabilities that we're calculating from the sampling distributions. But for now, you can look at it and say, boy, that sure is small. And because it's small, it means that that value, the p hat is equal to 0.66, is so far away from the center of that sampling distribution that it couldn't have happened by chance, because the probability of being farther away is very, very, very small. And when we see something like that, we're going to deem that statistically significant. There will be a benchmark later on down the road of 5% or 0.05. But for now, anything that looks small is more than likely statistically significant. But as you notice, this is not something that is a hand-wavy, gut instinct kind of discussion, but rather a very clear calculation and understanding of the value once you calculate it. As a second example, let's take something a little more cryptic. We're talking about numbers that are unlisted in Canada. They're saying 52% of all numbers are unlisted, yet from a sampling of 500 numbers, what is the probability that at least half of the numbers are unlisted? So from this, again, and you see that I've put it in bold this time because I'm really trying to hammer home the importance of justifying the use of these calculation techniques. If you satisfy random 10% and large counts, then we can say that the center of the sampling distribution is equivalent to the parameter of interest, which is 0.52. You can also show that the standard deviation of that sampling distribution is the calculation with the equation that involves the sample size n. So I've given you those values. I've shown you that the probability that more than half of the numbers are unlisted in that sample. So notice that p hat is greater than 0.5 is equal to, this is just an upper tail calculation at this point, using the values that we've calculated, and we get 0.8151, which is around 82%, but I like to give you different tastes of the way to interpret it. So in this case, I would say the probability that at least half the numbers are unlisted is approximately equal to 0.8151. So notice there is a process here. And in my class, I go by the process of state, plan, do, conclude. Well, to check the conditions is the plan portion of that for. The do, of course, is the calculations that we are now doing. The conclude is that final statement at the bottom of the slide. But certainly we're going to flesh this out a lot more when we get into significance testing. But you can see now where the confusion of this unit is really going to start to set in, because there's a lot of things that look similar to previous units, but now we're applying it in a different way. But it is all centered around this most important thing called the sampling distribution, that literally every model that we use moving forward is going to use when we're trying to come up with a statistically significant conclusion, or at least a value that allows us to make that inference in the end. So that's it for sample proportions. Good luck with your studies, and we will see you again when we talk about sample means.